The concept of electric potential tends to confuse a lot of students, and a small part of that has to do with the fact that we have two terms, one being electric potential energy and the other just being electric potential. It is a rather confusing way to kind of define these things, so I find the best way to try and explain that is with an example. And then we'll lead into a discussion about some of the concepts. But I'd like to start with this example first. I think it's a little bit more concrete because it relates to things we've already discussed. As I've mentioned, the concept of electric potential energy and electric force, and in general, electricity, to a certain extent, has a lot of parallels with gravity. So, what I'd like to look at is this concept that we didn't really discuss, but it's called gravitational potential, not gravitational potential energy. There's a slight difference, but just follow along with my example. So, we have the classroom, and we have a uniform gravitational field. We'll assume this is on Earth. If I place three objects of different masses, mass A, B, and C, being 10, 20, and 30 kilograms respectively, and they are located 1 meter above the ground. Now, what we've discussed to date is the concept of gravitational potential energy. The gravitational potential energy of mass A would be mgh, so it would be its mass times the acceleration due to gravity on Earth times the height above the ground, which in this case would be 98.1 joules. Mass A, which has 10 kilograms, would have 98.1 joules of energy at that location. Mass B would be the same equation, but it has 20 kilograms of mass, same gravitational field, same height. And if I multiply all that, I should get 196.2 joules. So mass A has 98.1, mass B has 196.2. Obviously, mass B has more energy because it has more mass. If I do the same for mass C, it would be 30 times 9.81 times 1. And if I calculate that, I should find that it has 294.3 joules of gravitational potential energy. Now you can see that all three of these masses at this given location in the same gravitational field have different amounts of gravitational potential energy. But if I wanted to take a look at, rather than just looking at the actual amount of energy for each individual mass, how much energy am I getting per kilogram at each of these locations? So I don't care so much that there's 10, 20, and 30 kilograms. How much energy am I actually getting per individual kilogram? So if I take a look over here and I take the gravitational potential energy at A, which is 98.1, and I divide it by the 10 kilograms, I should be able to find that for object A, I actually get 9.81 joules per kilogram that I placed at that point. Right? For every kilogram, I got 9.81 joules, so 10 kilograms gave me 98.1 joules of total energy. If I do the same for the gravitational potential energy at B, well, B, I got 196.2, but that's for 20 kilograms. So if I divide that by the 20 kilograms, I'll find that once again, I get 9.81 joules per kilogram that I placed at that location. If I do the same for mass C, divide that by the 30 kilograms that I had, once again, you'll find that I get 9.81 joules per kilogram of energy that I placed at that location. Now, it might be startling at first to see that each of these gives me the same amount of energy despite having different masses, but if we take a look, all three of these share the same distance from a reference point. They're all essentially being placed at the same height. The only thing that's changing is the amount of mass that I'm placing there. Now, rather than saying, well, the 10 kilogram mass gets me 98.1, the 20 kilogram mass gets me 196.2 joules, and the 30 kilogram mass gets me 294.3 joules, if I just want to take all the masses out of it and look solely at this line right here, a distance of 1 meter above my reference point being the ground, I should be able to say that for every kilogram of mass that I place anywhere along this height, this line that represents 1 meter in height, I will get 9.81 joules per kilogram that I place there. And that's a concept known as gravitational potential. It does not give me the specific amount of energy for a specific mass. Rather, it just gives me how much energy will I get per kilogram of mass that is placed at that location. One way to think of this concept of potential as opposed to potential energy is kind of like the cost per unit of energy, obviously, but we're going to say the cost per unit. So right now, if I take a look at two situations, let's say you go to the store, you're trying to, bake a cake, and you need eggs. All right, well, let's say you need like 30 eggs. You can either buy groups of 6 eggs, and they cost $6 in my example, or you can buy a package of 10 eggs that cost $8. Now, by default, your brain is already telling you which one to buy because you should be able to figure out, hopefully, which of these is actually the better deal per egg. But just so we can go through it, if I take the $6 and I divide that by the number of eggs, which is 6, what I'm actually getting is it costs me $1 per egg. Over here, I take my $8 for the whole thing, divide it by the 10 eggs that I'm getting, and what I actually get is this only costs me 80 cents per egg. This to me is a little bit more concrete. Plenty of people have probably done this, and when you've gone to buy something, especially if you're buying in bulk, you can sit there and say, well, if I take a look at these two, well, this I'm actually getting a cheaper price per egg, so 80 cents per egg versus $1 per egg. It's a little bit of an abstract analogy, but hopefully you get the idea that we're not looking at, well, I'm getting 6 eggs and it costs me $6. Ooh, I'm getting 10 eggs and it costs me 8. We're not looking at the actual amount or the actual number of eggs we're getting. We're looking at something that's a little easier to kind of analyze or compare, and that would be the cost per egg. So just to relate that to what we just spoke about, I'm not talking about the actual amount of energy. That would be the same as the actual number of eggs or the actual cost that I'm paying for that specific amount of eggs. Instead, we're just looking at how much energy do I get per kilogram? How much does it cost me per egg? All right, now gravitational potential, almost identical to electric potential. As I've stated previously, a lot of these things go hand in hand. So just to show you another similar calculation, we know that the electric potential energy from our previous video is going to be the charge times the electric field and the distance from a reference point. My reference point will be the negatively charged plate for this example, and I have 3 charges, charge A, B, and C, which are 1, 2, and 3 coulombs respectively. If I want to find the actual electric potential energy at any of those locations, I will take the charge of A, which is 1. I will take the electric field, which we are not given, but let's assume that the electric field here is going to be 1 Newton per coulomb to keep my calculations a little bit simpler. And the total distance will be 1. Hopefully you can see here that that will be 1 joule of electric potential energy. For B, I have 2 coulombs located in the same 1 Newton per coulomb field, 1 meter above my reference point. That will give me 2 joules. And from charge C, I have 3 coulombs in the 1 Newton per coulomb electric field located 1 meter above my reference point, and I get 3 joules. So for charge A, I get a specific amount of electric potential energy, same for charges 2 and 3. You probably see where this is going. If I'm more concerned with like that cost per unit, I can take my electric potential energy at A and divide it by the amount of charge I have, which is 1 coulomb, and that is just going to give me 1 joule per coulomb. If I take a look at the potential at, B, and I divide that by the 2 coulombs that I've placed there, I get 2 joules divided by the 2 coulombs. That will also give me 1 joule per coulomb. And if I do the same very quickly for point C, I have 3 coulombs of charge, but you'll find that I get 1 joule per coulomb. So rather than talking about the actual amounts of potential energy of a specific charge, I can say, well, these are all the same height above my reference point or the same distance above my reference point. So this line right here, if I remove all the charges, anything that I place on this line, I will get 1 joule of potential energy per coulomb of charge that I place at that location. So these numbers are easier. If I place 10 coulombs, I'll get 10 joules. If I place 100 coulombs, I'll get 100 joules. So rather than talking about specific charges, it allows me to talk about a specific location or specific point in the field and easily calculate how much energy I'll get per coulomb that I place at that location. So hopefully you're starting to see again that this has more to do with that idea of like the cost per amount. And I just want to relate right now 2 concepts that we've already learned. One concept we've learned and one we're in the process of learning. So electric fields, we know, are represented by a capital E, and that gives us newtons per coulomb. Now the reason it's newtons per coulomb is the electric field just shows us the amount of force per coulomb of charge that's placed at a given location. So if I take an electric field here that has a strength of 1 Newton per coulomb, well, if I place 1 coulomb of charge right here, I will get 1 Newton of force. If I place 1 coulomb of charge, I get 1 Newton of force. I get 1 Newton per coulomb that I place there. If I place 2 coulombs, I get 2 newtons. 3 coulombs, 3 newtons, and so on. But electric field is telling me the force that acts on a given charge when I place it at that location. Now, electric potential, which you guys actually probably know better as voltage, which is represented by a capital V. And this is voltage, the same voltage that you've seen on batteries and things like that. Electric potential is measured in volts, and as I've showed you before, it's just joules per coulomb. It's very similar to the electric field, but instead of being given 1 Newton per coulomb as the electric field strength, at a specific point, I'm given that the voltage is 1 joule per coulomb. So that just means that if I place a coulomb of charge here, I'm not concerned with the amount of force I'm getting. Voltage tells me the amount of energy. So if I place 1 coulomb of charge at that location, I will get 1 joule of electric potential energy. If I place 2 coulombs, I'll get 2 joules, 3 coulombs, 3 joules, and so on and so forth. So it's not as abstract a concept. You just have to remember, think about electric fields, which tells you how much force you get per coulomb, and electric potential is very similar, but you're just getting the amount of electric potential energy per coulomb. So electric field gives you force, electric potential gives you energy. It's just the difference of force and energy. A little bit more complicated because we're dealing with electricity and electric fields, but for right now, just understand force has to do with electric fields, energy has to do with electric potential. At the end of the day, they're very similar concepts. So as I stated, electric potential is the amount of energy I get per coulomb at a specific point. Much more commonly, we'll discuss something known as electric potential difference. And all that means is instead of talking about a specific point within this field, so maybe like this specific point, we're usually more concerned with what's the difference in voltage between those 2 points? What's the difference in the amount of energy we get? Same concept, but instead of looking at the joules per coulomb, we're looking at the change. How much energy, how many joules do you gain or lose per coulomb of charge that has been moved? So not a big difference, but electric potential difference. If you see that, we're still talking about voltage, but not voltage at a specific point in the field. We're looking at what's the difference between 2 different points. All right, so as we showed you before, if I go back to what I was originally doing, this concept of electric potential, you're really just taking the electric potential energy and you're just dividing it by the charge. You're just dividing the charge out. So instead of getting the specific amount of energy for that type of charge or that amount of charge, you're just given like the ratio of the energy to the amount of charge you place there. And that's all this is saying. It's the change in energy between 2 points, and you're just dividing out the specific charge. Now, if we actually think back and see that our electric potential energy is the charge times the electric field times the distance, we should be able to see here that charge times the electric field times the distance divided by my charge will cancel out, and you'll actually find that the change in voltage or the electric potential difference between any 2 points in a field is just the electric field strength times the distance that you've moved at. And this is all for a uniform field. So we've all looked at fields like this where everything's nice and uniform. So the voltage, again, V is voltage. The change is just the electric field strength times the distance that you have actually moved that charge through the field. And again, voltage, think of it like a 9-volt battery. This is essentially what you've heard. If you kind of connect any kind of device, you will have electrons that will flow, or electricity that will flow from one terminal to the other. Now, 9 volts just means that for every coulomb of charge, since 9 volts is the same as saying 9 joules per coulomb, for every coulomb of charge that flows from one terminal to the other, remember an electron is negative 1.6 times 10 to the negative 19th. So every electron that flows through, you get one of these. If you keep adding up electrons to the point where you eventually get 1 coulomb of charge, now again, that's a tremendous number of electrons, but if I keep adding these together, eventually I will reach 1 coulomb of charge. Once 1 coulomb of charge has actually passed from one terminal to the other, that means that 9 joules of energy has actually been expended, and that's all that voltage means. So the difference between these 2 terminals, well, one terminal has 9 joules per coulomb more than the other terminal. And that we'll explain further when we get to circuits why these electrons are moving and things like that, but it comes down to this potential difference. There is a higher amount of energy on one than the other, and much like a mass will fall from a higher energy to a lower, charge will move from a higher energy to a lower. That's getting a little bit ahead of ourselves for right now, and I apologize if that was a little bit over the top. But for right now, just understand that when you're given a uniform field and you want to know the potential difference, the difference in voltage, well, that's going to be the electric field strength times the distance between the 2 points that you're looking at. Now, to give you a more concrete example, let's take a look at example number 1. So if we take a look at example number 1, you're given an electric field that has an electric field strength of 200 newtons per coulomb. The difference between point A and point B is 1 meter. And you're asked, what is the electric potential? Again, it would probably be better to say, what is the electric potential difference between points A and point B? Well, this is a uniform field. You're looking for that potential difference, which we just learned is the electric field strength times the distance that that object has been moved. So if I take a look, I should be able to figure out that the difference here is going to be 200 newtons per coulomb times the distance that I moved it, which is, 1 meter. So what I will get is 200 joules per coulomb. And we ask ourselves, is this energy, is it being gained or lost? So if I'm moving a charge from A to B, is it gaining or losing energy? We assume a positive test charge since nothing's being given. So if I take a positive test charge and I move it from A to B, the positive test charge is going in the direction it naturally wants to go. So the best answer here would be minus 200 joules per coulomb. And all that means is if I took a coulomb of charge and I moved it from A to B, that charge would lose 200 joules of energy. So for every coulomb that I move from A to B, I lose 200 joules of energy, much like a mass doing what it naturally wants to do would lose a certain amount of potential energy. All right, very similar situation here, but now I'm looking at a field that goes from right to left. What I'm being given here is if the electric potential between points A and B is determined to be 45 volts, what must the electric field strength be? So we are given that the potential difference is 45 volts. We know the distance here is going to be 3 meters, and they're asking for electric field strength. Well, if I take a look, I know that 45 volts must equal my electric field strength times the distance that this has been moved. So if I plug this into my calculator, all I have to do is take 45 divided by 3, and I should find that my electric field strength is 15 newtons per coulomb. Not incredibly difficult. It's a fairly easy equation. The hard part comes in understanding when energy is being lost or gained, or when this potential is being lost or gained. And that we just have to go back to our original question. Would the charge, in this case a positive test charge, be doing what it naturally wants to do? We'll take a look at more of this in depth in class, but I hope this did a good job of getting across the general idea of electric potential.